Okay, when you flip over the can into cold water, describe what happens to the phase of the molecules in that can and the speed of the molecules in that can. When you flip it over, what happens to the molecules, the gas molecules, the X's and the O's, the waters and the airs? So let's talk about what you think is going to happen. I think most of you thought this about the same thing. So what would happen, let's say I have my can here. I have a can that has X's and O's in it. And let's say we have a lot of, almost everything is a gas in here. Okay, and then Javier, I'm going to flip this over. What do you think is going to happen to the phases of the molecules?
The air is going to slow down.
The air is what?
It's going to slow down.
Okay, so you're talking about speed. So the air molecules are going to slow down.
Because of the temperature change.
Okay, so if the temperature is lower, then what can we say about the speed of molecules?
It's slowing down.
It's what? Slowing down. Okay, so we're going to have slower X's. So let's say if they're moving, if we have big arrows for long movement here, we're going to slow down. What about the O's, the waters? What do you expect to have happen to those?
They're going to become water.
What?
They're going to become water.
Okay, so we had O's and now we have them down here in the bottom of the can.
They're going to join the other water.
The other water that's maybe still in the bottom of the can? Okay. And did they slow down too?
Yeah.
Remember when you acted out the different phases of matter? Which phase were you moving the most quickly in?
Yeah.
You were moving the most quickly in the gas phase. And how were you moving in the liquid phase? Do you remember that one? How did you move? A little bit faster, but not as fast as the solid. So in the solid phase, how are you acting?
Wasn't solid still?
Were you standing still when you were solid?
Not still, but it wasn't.
Who remembers how they were moving when they were solid?
Very slowly.
Very slowly. You kind of were like vibrating back and forth, right? Okay, so we have they both slowed down, and the water molecules became a liquid. Did the air molecules become a liquid? No, they didn't. So we have, this is something that I noticed a lot of you aren't talking about in your explanation of your can. You talk about the phase change, but a lot of you aren't mentioning the speed of the molecules inside when you cool it down. So the speed of the air molecules when you flip the can over. Make sure you talk about this on your poster, that those molecules are slowing down. And then another thing I'd like us to talk about is this idea of pressure and collisions. So again, think back to when you acted out those gas molecules, and some of you were acting as the container. How could you decrease pressure in that container? What are ways to make those collisions decrease? Because we know that collisions against the wall of the container are what actually cause that pressure. If you're not bouncing against the wall of the container, you're not causing any pressure on the walls of that container. So if we decrease the number of collisions, we decrease the pressure. So what are some ways you can think of to decrease the number of collisions? Tell somebody next to you, see if you can come up with 2 or 3 ways to decrease the number of collisions for a gas. Okay, so what are some ideas you have how we can decrease the number of collisions? Tell me one.
Space.
The amount of space? So what do you mean by that? Tell me more about that, please.
How many air molecules are in
Okay. Yes, I'd like to come back to this one and explain what we mean. So number of molecules. And I heard you talking about one other one.
Temperature?
Temperature. Okay, so these are 3 ways we could change the number of collisions. So now let's look at each one. How could we decrease the number of collisions with amount of space? How are we decreasing the number of collisions?
You could keep the same amount of gas, but increase the space.
Okay, and why would that cause a decrease in number of collisions?
Because there's little the same amount of gas, but there's more room for it to move. So they would less likely to run into each other.
Okay, run into each other, and what else?
And the outside stuff.
The outsides of the container, good. How about number of molecules? How could we decrease the number of collisions with number of molecules? What would we have to do? What do I have to do to the number of molecules to decrease the number of collisions, and why?
Decrease the number
Suck
of
the air.
molecules.
Okay, so take the air out or decrease the number of molecules, and how would that decrease the number of collisions?
Less likely each molecule would hit another one.
and
Because
The
there's
wall.
less.
the walls of the container. So we know that gases, they bounce off each other, they have these elastic collisions, but they also bounce off the sides of the container. And how about temperature? What do I have to do to temperature to decrease pressure?
Make it colder.
Drop, yeah, so the molecules won't be moving as fast as they will be moving if the temperature was hot.
Okay, good. And so I want us to look at a quick kind of video of this, so let's hope this works. We're going to see in here this container that has a top that can move up and down, and it has a certain number of molecules inside. And so we're going to see how we can increase the pressure or decrease the pressure based on those three things that you said: the amount of space, the number of molecules, and the temperature. Okay, so we have our air molecules here on the bottom of this container. And this blue kind of green line represents, it can like move up and down based on pressure. So if there's more pressure inside this space here, what would we expect to see? What?
Line and move.
Which way?
Up.
Okay, so the line will move up if there's more pressure in here. So let's first talk about, what's one of the ones we talked about, temperature. So right now inside this space, the temperature is 200. So if I move, somebody tell me a temperature to move this up to. I think it goes up to like 1,000 or something. So
900.
that might be a little high. So let's start with maybe 300. If I move the temperature up to 300, what do you expect to see these molecules doing and this blue line doing? Tell somebody next to you.
The molecule's gonna move slow and the lumpy.
I think it's pushing space.
Okay, so what are we going to see?
More movement and
More movement and,
pressure.
okay, so let's see. We're going to move it up to, oops, we're at 360.
Oh my God.
400.
Whoa, Nele.
So right here you see the V stands for velocity or speed. So when we went from 200 to 400, I didn't see what the original number was, but the speed went up, and then what happened to the pressure inside this container?
Line and up.
Okay, so the line went up, which is evidence that what happened to the pressure
Went up.
inside. What happened to the pressure outside this container? Did the pressure outside the container decrease? Okay, so let's put it back to how we started here. We had it at temperature 300 or 200, so we'll just hit reset here. Okay, so we're at temperature 200. The volume is, or the speed is, no, this might be volume. I thought, no, it's meters per second, so it's speed. So we have temperature, here's our volume. So temperature, speed, and we have some pressure outside this container, right? So right now, what can you tell me about the pressure inside the container and outside the container?
Even?
Are they the same, are they different, or are they
The
is
same.
one bigger
Oh,
and one smaller?
different.
What?
The outside is bigger
Why?
because the line is further down.
Okay, so the line is down. But if the pressures were, so Alicia thinks maybe they're different. Javier, what do you think? What do you think about the pressure out here and the pressure in here?
Yeah, they're different.
Okay, Justin?
It's not so many molecules outside, so shouldn't there be more pressure on the inside then?
Okay,
Isn't it the same?
interesting. So it's not showing us molecules outside. So let's say this is air out here and I have air molecules. Outside too. Okay, and they can put pressure on this container. Just like these. We don't have to draw arrows in these because we actually see them moving.
Yeah.
So there's air out here, there's a gas in here,
They're the same, right?
and this line is staying in the same place. So what can you tell me about the pressure that these molecules can do on the container this way, and that the pressure these molecules are putting on the container this way?
They're the same.
Okay, so raise your hand if you think they are the same. Raise your hand if you think they're different. So everybody thinks they're the same? So why are they the same?
Because if they're different, either or it'd be out more. But since they're still like maintaining the same, it's not either expanding or imploding. It's the same.
Okay, so we have this line that's not moving. The container wall isn't moving, we're not expanding, we're not imploding. So we can say that the pressure out here is the same as the pressure in here. Does everybody understand that? Because this isn't moving, and we know we have this battle. So if the pressure outside is more, then we'd see the line going down. If the pressure inside was more, we'd see this blue line going up. Okay, so now let's watch again. I'm going to increase the temperature to about 400 degrees, like you said. Watch what happens to the speed of the molecules, and watch what happens to the pressure inside the container, or the number of collisions. See if you can see if there's more collisions. Okay. So we saw that as we raised the temperature, the speed of the molecules changed.
The pressure's the same.
The pressure,
It's still the same.
so the pressure is still the same now because it stopped moving. But why, remember the line used to be right here. So why did it move up? What about the movement? So there was more movement of the molecules because the temperature went up. And so what did that do to the pressure inside the container? It increased it. And it expanded that container until, like she said, until we again reached this balance of pressures. So it's just like when you crush that can, you flip it over and you have this new battle of pressures. The can doesn't keep imploding forever. Or when you blow up a balloon, your balloon doesn't keep expanding forever. It reaches this point where it stops. Okay. And then let's go back, we'll reset it. And we'll look at the number of molecules, which was another thing that you talked about, is what changes the number of collisions inside of a container. So we're back to, this is our level. I'm going to mark it here so we know. What's going to happen if I decrease the number of molecules? We're maxed out at 400 here. So let's say I decrease the number of molecules in that container to 200. What will you expect to see? Tell somebody next to you.
More space.
I'm going to decrease the number of molecules in here. What's going to happen? Okay, so before I show you what's going to happen, let's quickly talk about the pressures here. What can you tell me about the pressure inside and the pressure outside the container? Are they different or the same currently? Okay, so right at this instant, are they different or the same?
Same.
Okay, and if I change it down to 200, what do you expect to see?
Line will go.
The line will drop because?
There's not as much molecules, there's not as much movement on it.
Yeah, there's there could be more molecules in the top and can be putting more pressure down.
Okay, so I currently have this much pressure out here, and this much pressure in here. It says the pressure is 1, but let's say you have the same amount of pressure inside and outside right now. Is the pressure outside changing ever?
No.
So what is changing? The temperature inside and therefore the pressure inside.
Yes.
So we're only looking at how the pressure inside is changing. The temperature outside is not increasing or decreasing, but the pressure inside is decreasing because that's what we're changing. We're changing what's happening inside here. So let's see what happens if I decrease my number of molecules.
Ooh. Less space now.
Less space where? In
Inside.
here. So the volume in here is smaller. Yep, it went down to 50. And the number of molecules was smaller. And what happened to the pressure inside the container?
It dropped until those equal pressure outside.
Okay, so it dropped. The pressure decreased. Why does he know that the pressure decreased at one point?
I don't know. I didn't see the process. So.
Okay, so let's watch it again. This is a really important thing that I think is kind of getting, it's kind of confusing because we have like this start, then we have what happens, and then we have the end. And at the start and at the end, we're saying there's equalized pressures because that blue line is not moving up and down. But what we have to watch is what's happening in between. So right now we're saying the pressure out here and the pressure in here are the same because we have this line staying the same. And now I'm going to decrease the number of molecules, and you're going to watch what happens to that line. Okay, so what happened to the line?
So it went down.
Okay, why did it go down?
There was less pressure
Less pressure where?
inside.
Okay.
There's less molecules.
Yeah.
So there's fewer molecules inside, which made the pressure inside lower because?
there's less space. I mean,
There's less molecules than like, so they're not, the molecules inside there are not putting as much as pressure
Where? On what?
on the line.
On
So
what?
that's-
On the line, okay.
Yeah, so that's why it dropped, because it
Yeah.
doesn't have the same pressure as it did when all the molecules were there.
Good. So, yeah, that's really important that you explain it. I think Fabian's explanation was really good right there. He said the pressure inside decreased because, somebody add on to this, let's restate it again. So he said the pressure inside decreased because, who can tell me why the pressure inside decreased?
Wasn't as much molecules. Wasn't enough.
Not as many molecules bouncing off each other and the walls of the container. So the pressure decreased. And then why did the line fall down then? This is the last part of the explanation that's really important. Why did the line fall down?
We had to find the place where the balance, where it was the same amount of pressure outside and inside the container.
And while it was moving, while it was moving, what can we say about the pressure inside and outside the container?
it was adjusting.
What? I heard a bunch of different things. What can you tell me about the pressure inside the container? Said it again.
You got me covered. So you know we're good right there.
Okay, what's happening to the pressure? Is the pressure in here and out here the same right now? What's more?
Let's try outside.
Outside is more. So
Yes.
we decreased the pressure in here. What happened to the pressure out here?
It was more increased. It became greater.
It was more because it was pushing down the
It's
molecules.
adjusting.
It says in a different way.
Okay, so yeah, and this is the part that we need to all agree on, because if we all choose a different way to explain this, it's going to make it confusing. So I heard some of you say the pressure outside increased. I heard some of you say the pressure outside stayed the same. What happened to raise your hand if you think the pressure outside decreased. I heard like half of you say it, so tell me if that's what you think. The pressure outside decreased.
Those heads were going.
Who thinks the pressure outside stayed the same? Who didn't vote? Okay, why not? Why didn't you not vote?
It's 11%.
You're not sure?
I don't think that it decreased or stayed the same.
I thought it
It
increased.
I thought it increased too.
I thought
Okay.
it increased.
Alright, increase.
Okay, so you think the pressure outside, was there, there's an option I didn't pick? Who thinks
Yeah.
the pressure outside increased? Sorry. Okay, so we have votes for increased, outside, or stayed the same.
The same.
So who thinks the pressure outside increased? Okay, and who thinks the pressure inside stayed the same?
Inside or outside?
I don't know, between
I
the
was,
same
I was,
and
yeah, we're talking about outside, right? Yeah.
Okay,
The same.
I'll ask it one more time, I'll get it right this time.
Oh.
Who thinks the pressure outside
Increased.
increased? Who thinks the pressure outside stayed the same?
Oh my god.
Okay, so we have maybe about 80% of you think it stayed the same, but a lot of you think it increased. So let's go with the person who thinks it increased. Why do you think it increased outside here?
Just had to have something to push it down to even it out.
Okay, so what's your evidence that the pressure outside was more?
The line dropped.
Okay, so that was pushing it down.
If it stayed the same, then the line would have just stayed, then there'd be more molecules moving, bouncing off the walls of each other.
Okay, and who thinks it stayed the same? And wants to explain why? Alicia, go ahead.
I think it stayed the same because the pressure, we didn't change the pressure, do anything to change the pressure outside, we changed the pressure on the inside. So since we changed the pressure on the inside, that became less. So that means that the pressure is outside is still the same, but it is greater than the pressure on the inside.
Okay,
Yes.
so I think kind of one way we could say is, let's say at the beginning here, let's say the pressure outside was 1 and the pressure inside was 1.
Yes.
Now let's say all of a sudden I drop the pressure inside to 0.5. Can the outside pressure stay the same and still be greater? Could it still cause this effect if I still put that as a 1?
Yes.
So who thinks that yes, this would work? If I change the pressure inside and I decrease it like in half, that the line would still fall down even though the pressure outside stays the same. Can this be true?
Yes.
Yes.
Okay. Does anybody think this can't be true?
Yes.
Yes.
Okay, so this is actually what's happening. We're not changing, exactly as she said, we're not changing the outside here. The outside is this air that's all around us. if you remember from your reading, it's 14.7 pounds per square inch. That's the pressure of this air all around us all the time.
53 pounds per.
14. So I could get out a scale later and we can look at what 14 pounds looks like. But it's probably a couple of, probably 3 of these textbooks, maybe 2. Well, I'll get a scale and we can look at it at the end of class.
On what?
On for every square inch of your body. So it'd be like stacking, if you could stack a book every square inch of your body, or two of those books every square inch of your body, that's how much pressure we have on us all the time. That's how much pressure is on this. It's a lot of pressure.
We're strong people.
But the molecules inside are also putting that pressure inside our body. We have gas molecules that are putting pressure out. And in this container, let's say we had all that pressure pushing down, we still had these molecules out. The pressure outside is not changing. But the pressure inside, as she said, is what we're changing. We changed the number of molecules. We changed the temperature. We changed the volume. So let's test your last idea here. And we'll just talk through this one quickly and then move on.
What's the last item?
So volume was your last idea. If we change the volume or the amount of space something has, it'll change the pressure.
Temperature when the.
Okay, so let's say I change this volume, and right now it's at 100. Let's say I change that volume to 200. So the space that it can take up is going to be bigger. Tell somebody next to you what you're going to see. The space. I'm going to change the space.
Wait, are you going to change the space going down or what?
Up. I'm going to increase the space. So what will we see when I increase the volume? So you're not going to see as much collisions. What else will you see?
The bar goes.
I'll move the bar up when I made more space for it. Yep.
Yes, but not changing the volume.
Okay, so let's see what happens. I'm going to change the volume to 200. I haven't tried this yet, so let's see.
She's happy. Oh, it's
Sorry.
non-selectable.
It's not letting me take.
Hello, beef.
Okay.
If you check that, then yeah.
Camera, that is what you call beef.
Oh my god. More water?
I'm moving the. I'm changing the amount of space.
No place.
Last collection?
So what happened to the pressure? Did anybody see what this pressure was before I moved
Yes,
it?
it was
1.
1.0.
It was 1. So what happened to the pressure?
It
It
decreased.
It decreased. And did I change the speed of the molecules?
You did not.
No, I just changed how much space they had to move around. So I moved the bar up because I had made more space for it, and we had a decrease in pressure.
Yes, ma'am.
Okay. I think that you're ready to talk about your explanations, finish your posters, but there's one more thing I want us to make sure that you know before you start. And that's this idea of water versus gas. So in this syringe, actually I didn't put 50, I put 35 milliliters of water, so
Super beef.
you can see that's full of water. And in this one there's 35 milliliters of air, and I've capped both of them. So I need somebody who thinks they're really strong to come demonstrate for the class.
Baby.
Wilson.
Come on, baby. Let her rip.
Baby, you're buff, man.
You don't have to be that strong, just a little bit strong.
Oh, Colin.
Because what if you don't do it?
She's a little strong.
Right.
That's nice.
Okay, so you're going to demonstrate for us? You can do it at your chair.
Oh, you don't know.
Okay, so I'm going to give him first. Which one do you want him to do first, the water or the...
Water.
Okay, so how much... It's at 35 right now. How much do you think that Cullen can push this down?
Barely anything.
34.
Like 2.
34, it's going to increase.
So you think he's going to be able to push it down 5 milliliters? No. Why not? Why do you think he's not going to be able to push it very far?
It's not strong.
Okay, let's say it's not about his strength.
Okay, there's not enough pressure applying against the water.
Okay, so why would that not be enough pressure against the water?
Because there's...
Water has a bigger pressure rather than air does, doesn't it? It creates more pressure than air.
Okay, so maybe water has more pressure than air. What else? What are some other ideas? What could you tell me about the molecules of water? So it's a liquid. They're closer together. Molecules of a liquid are closer together than the molecules of a gas. So let's give them a try. Let's see how far you can push this in.
Oh, my.
It should be sealed, but just hold it over the
I
container.
guess you can give it a try.
Give it all your strength.
Yep, it's just as I expected.
Heart, come on.
Can't even do it.
Colleen!
Okay, so it won't budge. What about this syringe of air?
Oh,
How far can you push this one down?
Shoot, it's like pushing air.
From 5 to 10, I think.
Okay, so you might be able to move it 5 or 10 or 20, down to 25. Okay. All right, give it all your strength, Colin. Okay,
You're
we
gonna
have to
blast
be
that
able
in
to
the shoulder
see
now.
your hands. How far can you get it
Don't kill me
down?
shoulder. Don't kill me shoulder.
Boom, man.
Okay, he got it down to 6 milliliters. So he had this column of water right here, and he couldn't compress it at all. But he had this column of air, and he could
And it still
compress
wasn't
that
enough.
air.
So,
So let's quickly
I already knew nobody could do it.
talk about these two syringes here. Okay, so let's say this is the plunger here. You're pushing down. This is going to be the water. This one's going to be the air. So, which one is this? Okay, this is the air one. Tell me if you could, like, if you had X-ray vision or, you know, like super magnificent microscope eyes, what would you see inside this air syringe?
Molecules.
And what would the molecules look like?
Move faster as
Moving far
balls.
apart.
Okay, so maybe far apart,
Yeah.
they'd be moving fast.
And there's like more
Okay, so there's more space in here between the molecules. And what would you see inside this one?
molecules bunching.
A lot more molecules with less space.
So they'd be more packed in here.
What do you have blocking that thing?
Oh, it's just a cap.
It's a marshmallow.
It never flies off.
It
Alright, push
takes
it.
a lot. So is that kind of what you're picturing here?
Yeah.
If I could, I'm just gonna make these smaller. All right. So now quickly before I let you go, let's talk about pressures here. When Cullen is doing this, tell me about pressures that's going on. Where is there pressure in
Little
this system
pressure going.
when he's doing this?
The pressure's
Pressure's-
decreasing.
So the pressure,
Is it increasing when
I
it
mean,
gets smaller?
it's increasing on
Yes, it's.
visually.
so he's pushing this in, and so it goes down. And we pushed all those air molecules in here.
Yeah.
Okay, and so what was he doing here?
Putting pressure.
So he was putting pressure here. And he was compressing the air between the space between those molecules. And are these putting any pressure back on him?
Yeah.
And so at some point he could not push it any farther, and so then what do we know about
The
the
pressure.
pressures? So once,
They're the same.
so yeah, once he couldn't put any more pressure, then we would say the pressures have equalized, or they're the same. And then what can you tell me about water? Is water putting any pressure?
Yeah,
The most pressure.
How do you know?
because
Because you can't push it down.
It's up all the space. And so you can put more pressure on it.
Okay, so there's not much space to compress those, and so we're putting pressure on here, and we get pressure back from the water. So the water is putting pressure back on Cullen's hand, right?
Yeah.
Okay. Some of you need to think about this in your explanation. For those of you who had water in your can, you need to think about the pressure that water would have in your can. Some of you, think about this pressure that water in your can could be putting on the can, and why that might make it so the can would not have crushed. I think that's it. So I want you to remember the things that we've talked about today up here. The first one is that when we slow down molecules, or if they change phase, that was decreasing the pressure because there were fewer collisions. So make sure you're thinking about that connection between collision and pressure. The second thing we talked about is that, does the pressure in the room change? So why would something collapse?
The pressure inside.
Because the pressure inside is decreasing. So think about that battle of pressure, but that as a class, we're saying that the air inside the room is not changing, the pressure out here isn't changing, it's the pressure inside that we're focusing on. And then the last thing is to think about the pressure that this water can put on the walls of a container too. Okay, so you're going to finish your explanations today. Most of you should still have your checklist, but if you don't, I'm going to leave this up here. I underlined this temperature and speed here because a lot of us weren't talking about this in our explanations, the speed of the molecules. And a lot of you aren't talking about this last point either. Our pressures inside and outside the can equal. So remember, we talked about there's the start, there's the end, but what I'm interested in is about why would it collapse, the middle part. And as you're working, I'm going to bring you around another paper that I think will help you finish your explanation of what's happening in each of those 3 cans. Okay, so go ahead and get with your groups. Your posters are over on the counter, the markers are over there. Okay, so for each of your cans, yours is going to be a little bit different than this, but we can talk about it.
Okay. Do one for each
Can. And so for the other groups who had, basically what it's asking you to do is for each can explain. So it says this can was different than the other 2 cans because it had, and you're going to say more or less of something than which other cans. Therefore, this can crushed more or less, and yours is going to be a little bit different because your sideways one didn't really crush, but you can try to explain it. Because the pressure inside the can decreased more or less when compared to the external air pressure, which either stayed the same, increased, or decreased.
Okay.
And then you're going to explain why you think that happened. Okay. So give it a try, see if it works for your scenario, but if not, you can use a similar format to explain your 3 cans.
More space.
More space? I thought we were looking at how much steam you had.
Oh, steam?
So
I thought when it crushed in.
as a group, you should probably decide because you said more steam, you said more space, and you said more liquid.
Oh, what the heck?
Oh.
So
I thought we were talking about when the can crushed.
we are, but which, you're doing can 3 here?
Yeah,
I'm in can number 3.
Oh, you're doing 2. Okay, so you said it has the most, does can 2 have the most space? After
Can
it
2?
crushed, it had the most, no, it had the least amount of space after it crushed.
Yeah.
But what I'm curious about is before it crushed. I want to know why, not the
before.
result. So this can was different than the other 2 cans because it had more what?
More,
Can number 2?
Yeah. What did this have the most of, or more what?
More,
We have to have the same factor.
more steam.
We're all doing
no,
steam.
less.
So
That's more steam than number 4 minutes.
you heated this one for 2 minutes, you heated this one for 4, and this one for 6. And in your picture here, it looks like you're showing me that it has the most steam, the most O molecules that are inside the can. Okay, so this can was different than the 2 because it had more steam than what?
Can 1.
1 and 3.
Okay. Therefore, this can crushed,
More.
okay, more, because
The pressure inside the can decreased.
more
Or more.
when compared to the external air pressure.
Pressure which stayed the same.
Okay,
The internal pressure changed
more.
more because
And that's what we need to figure out. So all of this, like what you just said aloud, you'll need to fix whatever, because everything you said aloud was right. This one had more of a pressure change than the other 2 cans, and you're saying it's because it has more steam.
more steam.
But why did that make this can crush more?
Because when we put it upside down, the pressure of the air molecules became less because the water was pushing into the air, those air molecules, and some of the steam became water.
Okay, so some of the steam became water.
Yeah, and so like once more water came in, the molecules, the air molecules went into each other, so they didn't have much space to go.
So when you're talking about the water molecules, you're talking about the ones that would come in through the bottom of the can?
Yeah.
Okay, let's focus on what we had in the can. So if you have the most steam in this can, and then you cooled it down and you said that steam becomes liquid, if this one has the most steam that became the most liquid, why would this can crush the most?
Because there's less pressure inside the can.
Why?
Because the liquid is covering like all in the can, so then most of the liquid is in the can, so then
So if the most steam becomes liquid down here, what happens to the pressure inside the can? And once that steam becomes a liquid,
decreases
the pressure decreases. Why?
because the air
There isn't as much steam molecules that when there was water. So now that all the steam molecules became water, there's less pressure.
There's more space, less
There's more space
pressure.
and less pressure
So why would this can crush the most?
because there's less pressure, and so since there's less pressure, the can will crush, so that the molecules won't. It will crush until the molecules will bunch into each other, so that the molecules will push into the can until a point that the can can crush anymore. So I can implode more.
Okay, so this one had steam that became liquid. This one had less steam, so who's doing can 1? So why did this can crush? Why did the pressure in there change less than the pressure changed in here? So this one crushed more, or crushed less than this one, so we know the pressure changed less. So why, oh, you had less. So why did it change less, do you think? When you cooled it down.
Because there wasn't a lot of steam that needed to base back, because there was more liquid than steam, and there was not a lot of pressure because there was not a lot of steam compared to number 2 and 3.
Okay.
And so therefore it was mostly so it was mostly liquid, less steam, not a lot, so there's a lot of pressure inside the can, and so therefore it didn't crush. I don't know.
Okay. So see if you can get that into words down here in your because part.
Was I right?
It sounded pretty good. I want to see, once you get it written down, like all the parts. And then what about you? You're doing this can? So this can, what do we have? It had what?
More steam, isn't it?
More steam? Did this can have more steam than this one?
Or no? Well,
This one was mostly evaporated. I'd say some of the steam evaporated.
came out. Most
Came out. So this one had less steam than
Number
this?
2, yeah.
Okay. And then both, okay. And so it crushed more or less than this can?
They say more, I say less.
We had 2 experiments.
Okay.
So,
So you have to decide which one you're going to answer. So did it crush more or less than that? That's what you need to decide and then explain why. Okay. So talk about it as a group.